This is standard 8FB4. We're going to construct a function to model a linear relationship between two quantities. Now, the problem they've shown us here is a car wash allows car owners to wash their cars by hand with a power washer. Costs for time spent washing are shown in the table. So here we've got a table of values, minutes washing, total cost. They want us to construct a function. It's going to tell you that down here. Write a function to model this relationship. Well, first off, let's see if this is a linear relationship. If it's a linear relationship, then what we know is that the slope, the change in y over the change in x, will be equal to constant values. Whatever it is, these will be constants, okay? If it's linear. Let's check it and see. Change in y over change in x. Here's our x, here's our y. Let's check a couple of these. Change in y here would be $325 minus $250, and that would give us 75 cents, 0.75. Change in x, 2 minus 1 would give us 1. Okay, so the slope here is 0.75, 75 cents. Let's try it among some of these others. We're not going to do all of them, but let's try another one. 475 minus $4 is 75 cents. And if I look at the change in x, that's 4 minus 3, which is 1. So we're talking still 75 cents over 1. 75 cents per minute of washing. We have the same slope for both of these. We're going to assume this is a linear equation. Write a function to model this relationship. We know when we're talking about modeling a linear relationship, it's y is equal to mx plus b. I don't know what the b is because I don't have 0 minutes here. I could work my way backwards and find b. Let's see. I know that the difference here was 75 cents. The difference here is 75 cents. The difference here is 75 cents. The difference here is 75 cents. So if I go back one more, I would subtract 75 cents from 250. If you subtract 75 cents from 250, what do you wind up with? Wind up with, let's see, $1. Oh, let's do it this way. Let's say borrow our 10. 10 minus 5 is 5. This gives me 4 here. I'm going to borrow 1 here. 14 minus 7 is 7. 175. Okay. So our 0 would be $1.75. It's $1.75 at 0 minutes. It's $1.75 flat fee. So our B is $1.75. That's what we start with before we add any minutes to our wash. Y is equal to, we've already figured out our change in y over change in x, our m. It's 0.75. So our equation is y is equal to 0.75x plus $1.75. That means we started at $1.75. Our rate of change is 75 cents per minute. So we started at $1.75. We add 75 cents for every minute that we wash the car. The second part of the standard, determine rate of change. Rate of change, that's your m, your slope. An initial value, that's your b, that's your starting point, of a linear function from a description, a table of values, and a graph. Let's start with the description. We're going to do one. Laurel owes her grandmother $2,000. She is paying her $25 per week until she repays the $2,000. Write a linear equation. Here it says a linear equation. To model the relationship between the number of weeks, W, since she started paying off the loan, and the amount of money, M, she still owes her grandmother. Well, let's start with our linear equation. Y is equal to mx plus b. Let's figure out which is our y and our x. The number of weeks since she started paying off the loan is W. The total amount of money is M. M is what we're looking for, the amount of money. Oh, they've used M here. Okay. M is equal to our slope, which is $25 per week. She's paying her $25 a week. We're talking about the amount of money she still owes, so she's going down $25 each week. W is the number of weeks, plus our B, that's where she started, $2,000. She starts at $2,000, she's going down $25 per week. You can put in the number of weeks to figure out the amount of money she still owes. What's the initial value for the model? It's 2,000. That's where she's starting. What's the rate of change? It is negative 25 because she's going down $25 that she owes each week. And that's what we're talking about. M is the amount of money she still owes her grandmother. What if we do this from a table of values? Look at the table below showing the volume of water remaining in a swimming pool that is being drained. Drain means it's going down in volume. And let's look at it. At time zero, there's 19,000 gallons. At 1 hour, there's 16,000. So we're going down 3,000 gallons each hour. Write a linear equation to model the relationship between the gallons of water left in the pool, G for gallons, and the number of hours, H, since it started draining. Our gallons is basically our Y. Our number of hours is our X. We start with Y is equal to mx plus B. Our Y is going to be G because that's gallons. Our X is H. Our B is where we are at 0 time, which is 19,000. That's where we're starting. Now we need our slope. Our slope, our M, our change in Y over change in X, our rise over our run. Change in Y here, 19,000 minus 6,000, okay? We're starting at 16,000, or we're starting at 19,000, okay? 16 minus 19, 1 minus 0. This gives me negative 3,000 over 1, which is negative 3,000. We're going down 3,000 gallons per hour. Our M is negative 3,000. Here's our equation. G is equal to negative 3,000 H plus 19,000. 19,000 is where we started. We're going down 3,000 gallons per hour. What's the initial value for the model? The initial value is 19,000. That's the number of gallons we start with. Initial means start. What's the rate of change? Negative 3,000 gallons per hour. We started with 19,000 gallons. Okay, now let's look down here. Let's do this from a graph. The graph shows how the weight of a puppy is changing over time. Write a linear equation to model the relationship between the weight of the puppy W and the number of days since she started plotting its weight. Well, on day 0, the puppy weighed 3 pounds. So let's start with our linear model. Y is equal to mx plus b. Our Y is our weight in pounds. We call that W. Our X is time in days. We call them that D. Now, we need our M and our B. Our B is where we start, our y-intercept. It's 3. Plug that in. We need our M, our rise over our run. We know M is change in Y over change in X. That's the same thing as rise over run. Okay, let's find 2 points that are on grid lines. There's 2. And we're going, let's look at our scales. We're going up 1 and over 1, 2, 3, 1, 2, 3, 4, 5. Up 1 and over 5. Okay. So our rise over run is 1 over 5. Let's see what 1 over 5 means. That's 1 pound each 5 days. What's the initial value for the model? 3. That puppy starts at 3 pounds. What's the rate of change? 1 pound every 5 days. And then the last thing we're going to do is interpret the rate of change and the initial value of linear functions in terms of the situation they model. What do these mean? Let's look at this one. The graph shows how the height of a houseplant is changing over time. This is the months. This is the height of that plant in inches. Write a linear equation to model the relationship between the height of the houseplant, H, and the number of months since it was planted, M. A linear equation is y is equal to mx plus b. Okay, in this case, let's see, our b, where we start, is 5. Our m, our rise over our run, let's find 2 points. Here's one on a grid line, here's one. We go up 2 and over 1, 2, 3, 4, 5. Up 2 over 5. Our m is 2 over 5. It's a rise over run. The x-axis is our months. The y-axis is our height. There's the equation. What's the initial value for the relationship? It's 5. And what does it mean? Well, let's look and see what it is. Let's read it on the chart. On the y-axis, 5 is 5 inches. The plant starts at 5 inches, right? Plant starts at 5 inches. What is the rate of change for the relationship, and what does it mean? Our rate of change is 2 over 5. When we talk about a rate of change, we're talking about the change in y over the change in x. Y is height in inches, so that's 2 inches. X is time in months. It goes up 2 inches every 5 months.